Thank you for the kind invitation. I'm going to be talking in this lecture about some topics that I've been working on recently around causality. So don't worry, there will be some kernels in there, but the focus will be less on MD and so on, and more on the problem of estimating causal effects. So when you're acting in the world, you're trying to figure out what's going to happen. This will be the topic of the talk. I should also say that I usually like to get questions during the lecture. So maybe now and then I'm going to pause, and if anyone has questions, please ask during. Of course, we'll have time as well at the end, but yeah, I'm also happy to take questions as I speak. So if at any point there is a question, you can raise your hand as well. I'm happy to answer. Great. All right. So I'm going to just start with a Simpson's paradox style example, just to illustrate some of the concepts we're going to be dealing with and to set out some of my terminology. So I'm going to give just a sort of simple toy example of a disease that's being diagnosed in a hospital. So let's say we've got some disease, and I'm going to call it X. And this disease can have like a mild form or a severe form, all right? So this is the two forms this disease can take in our toy example. Now, the doctors are going to look at the severity of the disease, and then they're going to prescribe a treatment. The treatment is A, and in our example, the treatment can be pills and it can be surgery. So pills more likely for the mild form, surgery more likely for the severe form. And then we're going to get an outcome, which is that the patient gets cured or doesn't get cured. And that's going to be a function of the disease severity and of the treatment that we've imposed. All right. Now, I can look at the historical data. So this process is going on for some time in my hospital. And I can gather the following statistics. So the probability of being cured under pills, under the treatment pills, is 0.8, and the probability of being cured under the treatment surgery is 0.72. So how is it that I get these numbers? Well, obviously, the treatment that I get is going to depend on the severity of the disease that I'm suffering. And so basically, let's say that I've received the treatment pills, right? If I've received the treatment pills, it's more likely I have a mild form of the disease, right? So here, which is the chance of being cured given the treatment, well, I've been given the treatment pills, so it's more likely I have the mild form. So I then have this probability that upweights the mild form, downweights the severe form, and then I have the chance of being cured given the treatment A and the severity. But I've given more weight to the mild form because I've taken the treatment for the mild form. All right, what about if I'd had surgery? Well, in that case, I'd give more weight to the severe form and less to the mild form. And then I'd weight my chance of being cured given treatment and severity over that different weighting. So this is how we get these numbers here. Now, let's say that I'm a hospital administrator and I see these numbers and I say, well, pills are cheap. And they work better. So now everyone's going to get pills. Okay, what's going to happen? Well, I'm now performing an intervention on the system. I'm introducing a new policy, right? The policy is everyone gets pills. Now, I'm going to use a different graphical notation for this, right? I've got my severity of the disease, and now I've got an intervention. This is a node with two boundaries around it. And then this y with a superscript a is the random variable y under the intervention a. So a is no longer a random variable, it's just an intervention. It's something that I'm saying is going to happen, which is that everybody gets pills. And you can see that this intervention is now disconnected from X, right? There is no arrow from X to the intervention because I've said everyone gets pills. I don't care. Got a mild form, got a severe form. I don't care, all right? I've kept on my graph, though, the random variable A, which is what the doctors used to do, all right? And there's a reason for that, and we're going to come to that shortly. But this is the historical A, which is no longer connected to anything we're doing. And then this is the intervention A, which is what we've imposed on our system from now on. All right, and under the intervention pills, the probability of being cured is 0.64. Under the intervention surgery, probability of being cured is 0.75. So they flipped the ordering. How do I compute these quantities? Well, I just take my chance of being cured, given treatment and outcome, treatment and severity, and then I just average that over my whole population because I'm no longer looking at the severity of the disease in order to determine my treatment. So this is the equation that I use. And so you can see that there is a difference between observing and intervening. Just because I observed this quantity here, where the doctors look at the disease and prescribe a treatment, doesn't mean that I'm going to get the same results when I intervene and give everybody a specific treatment. So I hope that from this example, you can see the difference between observation and intervention. and that you understand this graphical notation, which we're going to be using a few times in this talk, in order to sort of visually get the sense of how an intervention works and what it connects to. Great. Okay, so now let's think about what we're going to do in our talk. So some questions we'll solve is, first of all, just the average causal effect, which is this quantity here. We call this the average causal effect, or this quantity here is the average causal effect or average treatment effect. Why is it the average causal effect? Because I'm just averaging over my P of X. Okay. So now, obviously, just giving everyone pills is not the brightest thing to do. It may be that we can do something a little bit more interesting. So let's say that we're conditioning on our population having particular properties, and we're saying, well, what happens when we intervene on the population with those properties? So let's say that I've got this property V here, and V is blood pressure, right? And then I'm going to say, like, well, I'm going to I'm going to ask myself, what is the effect of intervening with blood pressure medication on the population with high blood pressure? Okay, so V, obviously, it connected to what the doctors were doing in the past, and it connects also to the outcome, because high blood pressure will determine how likely it is that I'm going to get low blood pressure after medication. But we've also got this interesting arrow here, okay? And the X here represents all of the patient covariates except for blood pressure. And the distribution of those remaining covariates will change depending on the value of V, depending on the blood pressure. So for example, let's say I have high blood pressure. Well, my age range is more likely to be in the 40 to 55 range and less likely to be in the 10 to 15 range. So the age demographics are going to depend on the blood pressure, right? And other things as well, like obesity perhaps, or other metrics here are going to change when we condition on having high blood pressure. And things like age and obesity will also have an effect on the chance that we're going to be cured. So we need to account for this in order to get the correct model of what's going to happen when we make an intervention on populations with these properties. So that's one of the questions we're going to be looking at, and that's the conditional average treatment effect, because we're conditioning, obviously, on V having some value. We can also think of a rather interesting question, which is a counterfactual question. So the question might be something like, of the patients who received one treatment, what would happen if we intervened to give them another treatment? So let me give an example. Of the patients who received surgery, right, historically, what would have happened had we given them pills? Well, let's work it through, right? They received surgery, so it's more likely they had a severe form of the disease. If we intervene to give them pills, it's not likely that they're going to be cured, right? It's likely they're going to stay sick, right? So this is one of these thought experiments we can do. So we're conditioning on the historical information here. We then find the distribution over X, and then we say, well, of the population with that distribution over X, what would happen if we had intervened? So this is a thought experiment. We can't take the pills out and then give surgery, that's not possible. But we can still run a thought experiment of what would have happened had we done something else. And that's an interesting topic to consider. Another topic to consider is maybe there's direct and indirect effects, right? So there's a direct effect from A to Y, but there's also an indirect effect from A to Y. So maybe, I take an anti-inflammatory medicine, so then I can do more exercise, and so then I get healthier, right? So is it that the anti-inflammatory medicine made me healthy, or is it that I'm doing more exercise and that makes me healthier? So this is a nice question I might be interested in asking. Finally, in the second lecture, I'm going to address the question of what happens if I don't see X? Now, as we've seen, X is enormously important, right? The doctors are using X to decide what to do. But if we don't see X, it's very hard for us to figure out what the doctors did. So in the second half of the talk, we're going to be looking at some interesting tricks that you can use in order to find out what's going on in this sort of setting where you don't see the context. This seems like it's very hard, right? Because if I don't see the context, how do I guess what the person is doing, right? I don't see, the context in which they're choosing to act. But there are some tricks, as we're going to see. All right, so those are the questions we're going to solve. Okay, so just to give the outline, in the first lecture, I'm going to be mainly focused on the case where I see X. Okay, and so we're going to talk about things like average treatment effect, conditional average treatment effect, average treatment untreated, so that's that counterfactual question, and mediation effects. Then in the second lecture, I'm going to say, well, what if I don't see the context? If I don't see the context, I need some additional side information. And we're going to be exploring the kinds of side information that we need in order to make inferences in this setting. Now, in causality, the problem of treatment effect estimation is a very old one. There's a huge amount of literature. What is it that we're going to do differently in this lecture? So generally in the literature, treatments have been binary valued. So I either get pills or I don't get pills. But in modern machine learning, treatments can be much more complicated. So maybe the treatment is a phrase, like a sentence, explaining like what you should do. So that's maybe the output of a large language model. And maybe the covariates are images like X-rays or MRI scans or something like that. So my treatment and my covariates and all of these things in modern settings can be high dimensional, can be complicated, and we need to use intelligently designed features of these high dimensional complicated things in order to run our algorithms. And this is what I'm going to be focused on today. I'm going to be using two different approaches, kernel features and adaptive neural net features. So I'm just going to split it as follows. So when I'm talking about the observed covariates, I'm going to stick with the kernel features. When I'm going to talk about the hidden covariates, I'm going to use adaptive neural net features. But I want to emphasize that you can use either kernel or neural adaptive features in all of the settings that I'm going to describe today. So you just choose what works for the problem you're trying to solve. And that's always a good philosophy. Great. All right. So luckily for us, we only need one like assumption and one algorithm for this whole talk. So this is all you need to remember for the whole talk. Okay, what is our assumption? Our assumption is that any function that we learn through this whole talk is going to be a linear combination of features. Okay, a weighted sum of features. Now, I might have a finite sum of adaptive neural net features, or I might have a sum of infinitely many fixed kernel features, right? So I could have either a finite feature dictionary or an infinite feature dictionary. If I have finite features, they're fixed. If I have finite features, they're adaptive neural net features. If I have infinite features, then it's a fixed feature dictionary. So the finite dictionaries here, I've given a couple of references. If I have an infinite feature dictionary, obviously I can't write down infinitely many features. So any algorithms that I'm going to define in respect of those infinite feature dictionaries are going to manipulate the dot products of the features, right? So basically, I need to express whatever algorithm that I propose in terms of dot products of features, because obviously, I can't write down an infinite feature dictionary. And fortunately for us, with the one algorithm we're going to use for this whole talk, this is going to be possible. All right. So this is our assumption. Our assumption is that any function is a linear combination of features. That's the only assumption that we need, or the only, let's say, algorithmic assumption that we need. Then there's only one algorithm that we're going to use, and that's ridge regression. So actually, to get a sense, could you raise your hand if you've encountered kernel ridge regression before? Excellent. Very good. So this is going to be just a quick reminder of kernel ridge regression. I'm going to talk about neural ridge regression in the next talk, but right now, just kernel ridge regression. So for the rest of the first lecture, kernel ridge regression is all you need. Okay, so remember the ridge regression loss function. I'm trying to predict y from a linear combination of features of x, and I have this ridge term here. All right, which is a L2 norm in the feature space of my function here, my linear final layer. Now, obviously, these features are infinite feature dictionaries, and these gammas are also infinitely long, so I can't write them down explicitly. I need to find some implicit way to express the solution of this ridge regression in terms of dot products. All right. Now, there is a theorem which tells us that the solution to this problem is always going to be possible to write as a linear combination of the features of my training points. Okay, this is the representer theorem. It's kind of easy to see why that's true, because basically like this linear dot product for any gamma orthogonal to the span of the training points is going to vanish. And then I'll just pay a penalty here, which I don't want to. So basically I know that I'm going to be left with this. Okay, so any gamma which solve this ridge regression is going to be a weighted sum of the features of my training points. And that's great because, well, guess what? I know how to take dot products of features of training points, they're kernels, right? So if this is true, right, then if I take the dot product of gamma with my features of xi, well, what's that going to be? This is just going to be sum over I of alpha I of the dot product of my features of xj with my features, to begin eraser, xj with my features of xi, which is going to be sum over j alpha j kernel xj xi, right? So immediately we kind of see that everything is going to be expressible in terms of kernels. Likewise for this ridge term, right? So the ridge term here, L2 norm of that is going to be basically using the same trick, sum over I, sum over j, alpha j, k, xi, xj. So all of the expressions in this term, all of the terms in this expression here, I can write in terms of dot products of features, and hence using kernel functions, and therefore the solution of my ridge regression can be expressed entirely in terms of kernels. All right. So, it's just a very simple expression here. I can solve it. And then this is the answer for my weights here of my features. And that's ridge regression. Okay. And if I want to make the prediction at a new point, well, that's also pretty straightforward, right? Because I've got my solution here, which is a weighted sum of features of xi. Let's say I want to predict the value of my function at a new point x. Well, I just take the dot product with my features of x, and then basically I get a dot product of my weights alpha, and then this vector here, which is basically a big long vector with entries k, xi, x. Right. So basically my prediction at a new point is going to be a weighted sum of kernels at my training points xi. So let's sketch that out. I've got like kernels there, maybe a negative kernel, really negative kernel. And so my function is going to sort of look like, it's going to be a sum of these things, and it's sort of going to go down and then go up. So you can get a sense of what that function looks like. So that's ridge regression. I'm going to write the ridge regression solution in a form that probably isn't as commonly used. So this is the form in which I'm going to write my ridge regression solution. And I'm going to write it as a weighted sum of y's with weights beta, which are k plus lambda I inverse k big X little x, right? That's the kernel between the training x's and the new x. This matrix here is the kernels between all my training points, and so on. So why write it as a weighted sum of y's? Well, we're going to see a little bit later why that is. But the expression that I'm showing you here is just the same expression as I had on my previous slide. I've just rearranged the terms a little bit to emphasize that the solution is a weighted sum of these yi's. Okay, so that's all that I'm going to talk about with kernel ridge regression. I will pause for questions at this point, just in case. Any questions? Good. Yeah, so this is, I think, mainly revision, and so hopefully it should be clear. Great. Okay, ridge regression. So now you know everything you need to know for everything I'm going to say for the rest of the talk. Okay, so we're going to start with just the average treatment effect or average causal effect. One can either use kernel features, and that's something we've discussed in this biometrica paper, where the authors are Rahul Singh and Yuan Chu, or we can use neural net features, where Yuan is the author. So I'm going to focus on neural net features, but I'm going to emphasize that we've got all the code online for both methods, so any of these that you wish to try, you can try. So let's return to the average treatment effect. So this expression, hopefully you'll recognize from a couple of slides ago. This is the average treatment effect or average causal effect, where we take our expectation of y, given the treatment A and the covariance x, and we just average over our whole population. We're not doing anything very clever here. We're just saying everybody gets the same treatment. We're going to make some assumptions. These assumptions are done here. I'm going to explain to you what those are. So the first assumption is the pill that I take doesn't cure you, okay? So there's no sort of spillover effect of treatments that I take on the people around me. So that's the first assumption I make. The second assumption I make tells me that I don't have a situation where there's a hidden like Z here, let's say, which I don't see, which is influencing A and Y, right? If this hidden Z is here and influencing A and Y, then obviously, everything I say is not going to work because I'm not correctly accounting for the context in which I'm acting, right? There's a Z here, which gives context to the data that I've gathered, and I am not able to see it. Well, then I'm in trouble. So I'm assuming that that's not true, okay? The final assumption that I make, this overlap assumption, basically says that I'm not going to make predictions about something that I've never seen. So let's say that people with severe form of the disease were never given pills, or that people with mild form of the disease were never given surgery. If that's the case, then I have no idea what would happen if I gave people with the mild form of the disease surgery. I've never done it, so I can't predict anything about anything that I've never done. So, one can weaken that assumption, but at that point, you're extrapolating. You're looking at data outside of the data that you've used in training. And there are ways to do that, but we're not going to explore those in today's talk. So these are the assumptions we're going to make, and I'm going to remind us of these a little bit later when we're going to talk about hidden context, but for now, I just state those. Okay, I'm going to illustrate this causal effect estimation example with a US Job Corps data set. So that's a training program for disadvantaged youth in the United States. So in that case, the treatment that we give is the number of training hours that the students have undergone. The context is everything we know about the individual. So what is their age? What is their marital status? What previous education have they had, et cetera, et cetera. And then the outcome is the percentage of employment. So what is the chance that they're employed at the end of this program? So obviously, an efficient use of resources gives the right number of training hours to maximize the prospect of employment at the end of this program. So we need, first of all, in order to do the average causal effect, to get the expectation of the outcome given the A, the treatment, and the X, the covariance. So that's the first thing we need to. Yeah, there's a question.
Maybe before you continue, is there any justification for these assumptions in this actual case that you're going to study?
Yeah, so in this case, in fact, all of these assumptions can be questioned. For instance, like, if I'm part of a community, then maybe the treatment I'm getting does influence the people around me in a local sense. So it might be desirable to weaken that assumption. And there may be, let's say, covariates that we're not accounting for that are influencing the effect of these treatments. So I would say, these examples, or in this specific example, one has to be very careful about these assumptions. Ultimately, the only, let's say, valid way to test those assumptions is to draw conclusions and then to act according to them. So if I believe that a certain treatment is going to increase employment, and then I impose that treatment as a policy, and I don't get the answer I was after, then I've made a mistake, and I have to go back and say, okay, what assumptions did I get wrong? So for sure, in this case, these assumptions, as strong assumptions, they may not hold perfectly. They may hold well enough to give us meaningful conclusions, but the only way to really test them is to, let's say, act according to them and see what happens. Yeah.
Okay, thank you.
Great. Yeah, so our goal here, right, we want the expectation of Y given A and X, right? So the percent employment given the covariates, so the marital status, the education level, the age, and so on, and the treatment, which is the number of hours in this training program. So obviously, we've run this training program for a while, so we've seen some previous treatment that's been applied, and that treatment has been applied according to these covariates. But now we're looking to do interventions, so we're looking to see what happens in the future when we modify our program. So, right, we've got this conditional mean of Y given A and X. So how many inputs do we have? Well, we have 2 inputs. When I talked about ridge regression, I had 1 input, not 2 inputs. So what do? I'm going to do a particular thing, and I'm going to explain why I do it later. I'm going to say that I've got good features of X, and I've got good features of A. I've got a kernel on X, I've got a kernel on A. So I emphasize, by the way, that the argument of the feature determines what feature map I'm using. I don't need to use the same feature map for X and for A, but I didn't want to have a million subscripts. So instead, I just used the argument of the feature to identify the feature. Okay, so I've got good features of X, got good features of A. How do I combine them to get features of X and A? Well, what I'm going to do is I'm going to take the outer product or the tensor product of these features, okay? So this gives me a big feature dictionary where each entry is basically feature I of A times feature J of X, right? So it's sort of the product of all pairs of features. That's a very big feature dictionary, and that's the feature dictionary we're going to use. We're going to use that because we need to use it. It's a modeling assumption we have to make in order for everything that I'm going to say to work. But it's also, I would say, in the kernel setting, not necessarily too bad of an assumption. So let's say that I'm using an exponentiated quadratic kernel. When I use that representation, I'm actually getting a space of functions which is dense in the space of continuous functions on A and X together. So that's a pretty big space of functions. So it's not hurting me too much to do this. Now, if I do this, then my kernel is going to just be the product of the kernels on A and X. So every time I saw a kernel of X before, I now see a kernel of X times a kernel of A now. So pretty easy, right? So everything becomes very easy to translate from a single input to a pair of inputs, which is what I'm dealing with here. All right. So what does my ridge regression solution look like? Well, my solution is still a weighted sum of y's. So remember, I'm using that slightly unusual representation of the ridge regression solution, where my weights are going to be just the standard weights for ridge regression, but where I had before just a kernel matrix on X, I've got an entry-wise product of the kernel matrix on X with the kernel matrix on A. Pretty straightforward. Okay, and then predicting at a new point, well, I've got the kernel between my training A and my test A, entry-wise producted with the kernel between my training X and my test X. So ridge regression solution is pretty straightforward for this case. So we've got this. Now we need to integrate it over P of X in order to get our average treatment effect or our average causal effect. So what is this? Well, I just take this quantity here, the gamma naught. The gamma naught is my estimate of my conditional mean of y given Ax. I take its expectation over X, and that's it. I'm done. I'm going to take one more step, though. This step is completely useless for this example, but it's going to be useful later. The one more step is to take the expectation inside the dot product. Okay, I can take the expectation inside the dot product because of this bilinear form of my feature dictionary, right? So that means that an equivalent way of writing this prediction is as the dot product of gamma 0 and the features of A outer producted with the expected features of X. So the vector of expected features of X. And this is what we call the mean embedding. It's like a representation of the probability of X in terms of a long vector, in fact, an infinitely long vector of expected features of X. So, doing this expectation outside or inside the dot product here doesn't make a whole lot of difference. But I'm sort of showing you this example to alert you to the fact that you can take the expectation inside the dot product in this instance because of the form of the feature dictionary that we're using. So then, what does the regression solution look like empirically? Well, it's just the average of my ridge regression solution on A and X over the xi, which are the points that we've observed drawn from X. So the expression is just a single line. It's very easy to do the average causal effect when you're doing kernel ridge regression. So now let's look at what this looks like on the Job Corps example. So here's the result. Number of class hours here, percent employment here, so higher is better. And what we're seeing here is like a property of diminishing returns. So let's say, we're an academic and we do a master's and then PhD, then postdoc, faculty position, professor. So yeah, we're also comparing against another method. What you're going to see here is like this method is a little bit more jagged. And we'd argue that the, let's say, prior assumption that we're making in using kernel features is that we have smooth functions. And this assumption, at least, is a reasonable, hopefully, and plausible assumption to make in the setting that we're considering. This is generally, by the way, the setting in which you should be using these kernel methods. It's like you don't have too much data, it's not in too high of a dimension, but the functions are assumed to be intrinsically smooth. In this case, kernel methods are a pretty good bet. And so that's the methods that we're going to be using for these examples. So econometrics data is actually a pretty good fit for kernel methods. Obviously, some of the examples we're going to be looking at in the second lecture are going to be much better suited to neural nets, and we're going to get to those in due course. But for now, in these econometric settings, we'll stick to the kernel approaches. Right. So that's all well and good. Now let's think about a slightly more interesting problem. So the conditional average treatment effect, where we're conditioning on some V, right? In the medical case before, this was like high blood pressure, and then this was everything else, like the age and the obesity and whether they've got diabetes and so on and so forth. All of the stuff that could be interrelated with high blood pressure. Just to explain some notation, this arrow with the two ends means that I take no position about the causal influence of V and X. So it could be V causes X, could be X causes V, could be there's a hidden common cause, I don't know, I don't care. There's just some relation between them, which I have no position on, all right? So obviously, both V and X determine the treatment that was received historically. So the data that we've gathered has been gathered with V and X in mind. The outcome is going to depend on V and on X. And then we're going to do some intervention conditioned on V. Okay, so this is like the intervention of giving blood pressure medication to people with high blood pressure. Okay, the conditional average treatment effect is the conditional mean of the random variable y under intervention A, conditioned on V taking some value. So before I had a function of 2 arguments, now I have a function of 3 arguments. Well, no surprises. Basically, I'm going to use this Kronecker product of all 3 features as my representation of my feature map for that triple of variables. And we're going to see shortly why that's necessary. So at this point, I need to take a conditional expectation. How do I do that, right? So there is a hard way to do that, which is to try to learn the conditional density of X given V, right? So perhaps I'd look at all my data, and then I'd learn a diffusion model that learns to sample X given V, and then I'd use the samples from that model in order to get my conditional expectation. But that seems that you're solving a harder question than you need to, right? Because X given V, well, X could be very high dimensional. It's like all of the demographic information we have about our patients. So learning a generative model of this very high dimensional object seems to be a difficult thing to do. Why do something so difficult, right? Because all that we need is the conditional mean of the features of X, right? We're predicting from these features. Don't just learn to sample all of X. Just learn the conditional feature mean and deal with that, right? That seems to be a much easier and simpler thing to do. So this is exactly what you do. Remember, because of this notation here, we can move the expectation inside the dot product. So this is the same trick as we did for the average treatment effect, but now it's actually useful. It's not just a little game. It's something that's actually helping us. And then what we get here is the conditional feature mean of features of X given V. Once we've got that conditional feature mean, we just plug that into our regression, and that gives us our conditional average treatment effect. So the next question is, how do we get a conditional feature mean, right? What is the problem that we need to solve in order to compute the conditional mean of features of X given V? And remember that this is not an easy problem, because in the example that we're talking about, we're using kernel features. So I'm predicting infinitely many features of X given V. That's a lot of features. So what do we do? So in this slide, I'm going to talk about what we do in order to learn this big, long vector, so to speak, of infinitely many features of X given V. So I need to have an operator. So think of this as a sort of matrix, but infinitely large, which is mapping from my V features to my X feature space. Okay, so before, if I'm mapping from features to a scalar, well, it's just a function, but now it's an operator because I'm mapping from feature space to feature space. So think big matrix is a good way to sort of conceptualize it. And if I take this big matrix and I apply it to my features of V, then I get my conditional feature mean of features of X given V, which I'm going to denote by this notation here, mu of X given V. So if I learn this operator, I'm going to need to make some assumptions on that operator. It has to live in some space. What's the space that it's going to live in? Okay, so I'm going to say that this operator lives in the span of the outer products of features of X and V. So at least conceptually, you can see that that makes some sort of sense because the dimensions are right. I'm getting an input which is in V space. I'm getting an output which is in X space. This notation here means that my operator has a sum of squared singular values that is finite. So it's sort of like a well-behaved operator which has fast decaying singular values. So it's an infinitely sized matrix, but its singular values decay fast. So this modeling assumption is a little bit hard to conceptualize, but I can interpret it a little bit more easily as a smoothness assumption on the functions that I'm after. So what is this smoothness assumption? This smoothness assumption says that if I'm taking the conditional mean of any function of features of x given v, this should be in the feature space on v, right? So I'm sort of saying that the conditional mean of any function of features of x should smoothly change as the conditioning variable is changing, right? My conditional mean changes smoothly as the variable that I'm conditioning on changes. So this is a reasonable smoothness assumption, right? If I change my conditioning variable by a tiny amount, and then the conditional mean changes by a huge amount, well, that's very hard to learn because I need to like gather a gigantic amount of data in order to model all of these jumps in my conditional mean. So instead of that, I'm going to make a smoothness assumption on the conditional mean. And so we're going to call this operator a smooth operator. Sorry. How do we learn this smooth operator? We're going to solve a regression function, which is this regression function here, right? I'm going to learn the operator mapping from features of x to features of v, sorry, to features of x. I'm going to make a constraint. This constraint is exactly the ridge constraint for operators, so sum of the squared singular values. If f were a matrix, it would be the sum of the squared entries of the matrix, same thing. So this is great because I said right at the start that ridge regression is all you need. Well, I'm doing ridge regression again. The only difference is that I'm doing ridge regression to an output space that is infinite dimensional rather than finite dimensional. And then this norm here is well defined because I've assumed that my f is in the space of Hilbert-Schmidt operators, which means the norm is well defined. So I've just done ridge regression from a feature space, which we're used to a feature space, which is a little bit more surprising. So I'm mapping to infinite features. Like, what does my solution look like? Is it that I need to write infinitely many ridge regression problems down? Well, no. All that I need to remember is that my ridge regression solution can be written as a weighted sum of the outputs, right? Remember that before this was yi, right? And this was yi. Well, now these are features of x, but I'm taking a weighted sum of those features with exactly the same weights as before. So in other words, under our assumptions, mapping to an infinite space of features is no more difficult than mapping to a single scalar. And you can kind of think of it as, I'm doing mapping to each of the entries of this infinite vector using the same set of weights. That's a way to understand it. All right, I'm going to pause here. Are there any questions about this? No questions. All right. So where I'm going with all of this is that I'm learning to get the conditional feature mean of x given v in order to get my conditional average v mean effect. I'm going to do one little indulgence here, so which is one slide of theory. So if you need to check your email, now might be a time, but it won't be long. So I'm going to demonstrate that even though I'm doing ridge regression to infinite dimensions, I can still give some convergence guarantees. So this is another advantage of using kernel methods, is that there are some really, really nice and well-established convergence guarantees that you can apply to your methods. And these apply even when I'm mapping to infinite dimensions. All right. So basically, here is my smooth operator. And I'm going to say, well, my operator might be, less smooth or more smooth, according to this thing called C1 here. So basically, I'm sort of saying I'm starting with a function which is Hilbert-Schmidt, and then I'm smoothing it a bit more by this t, which is my covariances of my features of v. Okay. So if you're not familiar with the details of that, don't worry. The point that you need to understand for this slide is that c is in the interval from 1 to 2, and as c goes up from 1 to 2, the problem gets more smooth and therefore easier, right? Learning a smoother function is easier. I need less data to do it. Okay. I also care about how large the space is I'm mapping from, okay? And so to do that, I look at the eigendecay of my covariance of my features of my v. If it's got a super fast decaying spectrum, I'm effectively mapping from a small space. If it's got a very slow decaying spectrum, I'm mapping from a big space, okay? And so, b, if it's small, problem's hard. If it's very big, my problem's easier. Okay. And then based on, my c and my b, I have convergence of my e in Hilbert-Schmidt norm. And so this is really nice because it's sort of telling me that as I see more data, my estimate of my e is going to converge to my population e. So this is very nice. This is a very simple version of this convergence result. There's a more complicated version of the convergence result in the event that my function is outside of the modeling space. So if my function is sort of somewhere between my Hilbert-Schmidt space and the space of square integrable functions from V to X. And so that I'm going to leave for people who want to read the papers, but I just alert you to the existence of the result. So now you can stop checking your email. Here is the empirical solution to the conditional average treatment effect. And it's actually, again, like it's very easy to understand. So remember the conditional average treatment effect. I'm sort of saying that I need my conditional mean of y given, y with intervention A given v equals little v, right? So I'm looking at the population for whom v takes some value, okay? Now this part here is basically just my regression of y, a, x, and v, right? So this is regressing from ax and v to y, but then I need to take the conditional mean of that quantity over x given v equals v, right? And the part that does that is this part here, right? This part here is, you can see just by the form of it, the conditional mean of x given v. And so if I sort of put that in here, and then I compute this with this conditional mean, then I'm getting out my conditional average treatment effect. So this expression here is basically the empirical version of the trick that I did a couple of slides ago of taking the expectation inside the dot product as I've done here. So, the sort of important upshot of this, the upshot of this is that, once again, the conditional average treatment effect, I can write just in one line, just using kernels. So it's actually a very simple and very straightforward thing to do, despite it being, let's say, conceptually quite a complicated object that we're talking about here. Once again, you can get a consistency result. The consistency result combines a consistency result on this conditional mean with a consistency result for the mapping from x, v, and a to y. Okay, this is probably not the best bound you can do, but this is a bound that we have. So and you're encouraged to do it better. But obviously, these take exactly the form that you'd expect, which is the standard form of the bounds for ridge regression. All right, so now let's look at a conditional average treatment effect example for the US Job Corps data. So X is all of the covariates that we have, except for age. So basically, we've got age as our variable we're going to condition on, and then we're going to look at the treatment conditioned on age, or the effect of the intervention on treatment conditioned on age. So, obviously, and just conceptually, you can understand that knowing the age is going to tell us a lot about the remaining demographics. So, right, if somebody is 26-year-old, they're more likely to be married than if they're a 16-year-old. And, education levels are also going to depend on age, and so on and so forth. So, yeah, like the distribution of X is going to change when V changes, and we need to correctly account for the shift in distribution in order to correctly predict the effect of the intervention A on the population where V takes some value. So that's what we're going to do now. We're going to use the formula that I showed you on the previous slide. And what we're going to get now is quite an interesting result, which is a contour plot where we've got our intervention on our x-axis here. So this is the number of class hours that we're requiring our students to take. On the y-axis, we've got age, right? And what we're seeing is that we can sort of slice this plot at different ages in order to see the effects of different interventions at that age. So for example, 16-year-olds have employment that increases from 28% to 36%. So if I slice here, I get an increase from 28 to 36, and then it goes down again. 22-year-olds here, I can slice and I get from 40 to 56. So this is interesting. Like if I've only got a limited amount of money to allocate to these training programs, then maybe I need to think a little bit carefully about how I'm going to split that resource allocation across different age groups in order to get the most bang for my buck. And that's what I'm showing in this plot here. So if I'm a policymaker, a plot like this might end up being very useful to me. Great. So that's conditional average treatment effect. Any questions about that? Okay. So now we're going to do an example together. So this is the average treatment on the treated. So remember what that was. It's like, of the patients who received one treatment, what would happen if we intervened to give them another treatment? And I'm going to remind everyone what that feels like for the example we started the talk with. So of the patients who receive surgery, they are more likely to have a severe form of the disease. What would happen if we gave them pills? Well, probably they wouldn't be cured, right? So this is the kind of thought experiment that I'm describing here. So I'm going to look at my historical A. I'm going to get the distribution over X given that historical A, and then I'm going to compute the treatment effect for that distribution. Okay, so what does that look like? Well, first of all, remember up here that this is going to be equal to gamma 0 and features of A tensor features of X, right? This is the form that this is going to take. So next step, well, we need this conditional mean of Y. Let's see. So I'm actually going to write it the following way. E gamma 0, right? Features of A prime, right? That's our intervention. This is the new treatment that we're proposing for the patients who receive the old treatment A. So A prime is the new treatment, A is the old treatment. And then I'm going to do the tensor product of features of X, right? And I'm taking the conditional mean of this quantity here, given the historical A took some value, right? So my random variable here is X, right? Because this A prime is not a random variable, that's my intervention. And what's the magic here? Well, we just have our gamma 0, and then we take the expectation inside the dot product, right? So my intervention is the same, it's not a random variable, but then I take the conditional mean of my features of X given A equals A, right? So I take my conditional feature mean, so this is the result of a smooth operator, then I plug that into this regression here, which I get from regressing Y on A and X, and then this gives me my average treatment on my treated. So this counterfactual of what would happen if I intervened with treatment A prime for patients who receive treatment A. So now let's say that I wanted to compute this using data, right? What would that look like? So again, like what I really want to emphasize here is just how easy everything that I'm describing is. So everything can be pretty much written in a single line. It's very, very simple to do this stuff. Okay, so I'm going to have, I'm regressing to Y, right? And I'm regressing to Y from A and X. So what I'm going to have is something like, K, AA, KXX. So this is the entry-wise product of kernels on A and kernels on X plus lambda I inverse, right? So that's my regression from X and A to Y. But now I'm applying that to my conditional feature mean of X given A, right? So, well, first of all, I'm going to have my K big A little a prime. So that's the intervention that I'm making. And then what am I going to have next? Well, conditional feature mean of X given A. So I'm going to have KXX. Then I'm going to have KAA plus lambda 2I, different lambda because different regression, inverse, then KA little a. Sorry. Yep, that's right. So basically what I've done here is I've regressed from my, my little a that I did my original treatment on to X. Okay, so I've found out that my patients who received surgery have severe form of the disease, and so that's what I've done in green here. And then I basically said, well, what happens if I intervene to give a new A to the patients with that distribution over X? Okay, so the patients who've got a severe form of the disease, what happens when we give them pills? And that's what this, determines. So what I emphasize here is I just wrote that on the slide now. So this is to show you, like, once you see these tricks, it's very, very easy to like do them over and over again. So are there any questions about that? So conditional mean of features of x given a, and then I'm going to plug that into my distribution of y given a and x, and that's it. So very straightforward. Okay, so that's the average treatment untreated. And here I can skip forward a little bit. Let's go now to mediation analysis. So this is the final example that I'm going to cover today, and it's also the one that's sort of most mind-bending in some sense. So what I'm going to do is I'm going to say, well, I've got two paths from A to Y. I've got one direct path and one indirect path. So the example I gave here, anti-inflammatory medication, better health, or anti-inflammatory medication, then more exercise, then better health. So basically, I'm interested in which of the paths is the more important path. Is it the direct path? Is it the indirect path? So again, this is something that I might be very interested in as a practitioner. All right, so now I'm regressing obviously to Y, but I'm regressing to Y given M, right, the indirect path, given A, the direct path, and X, of course, my covariates, right? So I've got, again, A from 3 arguments. We know how to compute, I've got Y from 3 arguments, but we know very well how to compute Y from 3 arguments. We've done it many times. Yeah, that's pretty straightforward. Now here, I'm going to introduce a quantity called the mediated effect. Now this one, like, it took me a very long time to understand what's going on here. So I'm going to do my best. Basically, what is this? It's got two things coming in here. It's got an A prime in orange, and then this M superscript A, okay, M in red. Now A prime is pretty straightforward. That's the effect of an intervention A on Y, right? I've made an intervention, it acts on Y. We know what that means. This thing here is more interesting though. This is a distribution over M given another intervention A. So basically what that means is this is the way in which the distribution of M can change as I change A. So that's sort of the set of distributions over M that I'm allowed to see. All right. So, maybe if I'm giving anti-inflammatory medication, I'm going to exercise for 1 more hour a day, but I'm not going to exercise for 10 more hours a day. So it's a set of plausible distributions over M that I'm able to attain by varying A. I can't go like crazy. I just have to look at the distributions of M that I can attain. Okay, so in a sense, I'm saying, well, look, I'm adjusting M, but I'm only adjusting M in the ways that I'm allowed to by changing A, and I'm also intervening directly on Y. But the change in this distribution, I'm doing independently of the direct effect of A on Y. So I'm changing this distribution in ways that are not directly the same as the changes that I would get if I was using A prime to change M. Why is this interesting? Well, it means that I can sort of say, well, I'm going to change M in a way that I could never do in reality, which is I'm going to change M in a way that doesn't depend on the A that I'm using to affect Y. So sort of say I'm giving, I can do an experiment like I give anti-inflammatory medication to my patient, but the patient does the same amount of exercise that they would do if they had no medication. So that's the kind of thought experiment I'm doing here. And this quantity here sort of embodies that idea. So are there any questions about that? Or that's okay. Great. Now, lucky for us, this quantity here can be computed very simply using all of the tricks that I've talked about so far. So it's like easy enough that I'm not going to do it, but I've got a conditional feature mean of M given A and X, right? That's the conditional distribution of M under green A over X. And then I've got also my intervention A prime, which is the direct effect on Y, and then I compute this. So again, it's just a single line of math when you're implementing it using kernels. It's very, very simple. So nothing is difficult here. All right, so let's now look at an example in the job corps case. So in the job corps case, what we're going to do, we've got X, which is all of our demographic information. M is a mediator. So that is now what Y used to be, right? Which is the percent employment. So M is the percent employment. And then Y here is basically the chance of being arrested. So obviously, ideally, you would want the chance of being arrested to be low. But the question is, is the chance of being arrested low because you did the course, or is the chance of being arrested low because you got a job, right? That's the kind of question that we're going to answer here. So again, if you're a policymaker, that might matter. So here is the number of class hours that determine the percent employment. So that's on this x-axis here. So the x-axis class hours will determine the distribution over the percent employment. And we've already seen that class hours have a pretty strong effect on percent employment. And then this is the effect of class hours that is going to directly influence the chance of being arrested on this axis here. So that's something we haven't yet seen. We're going to first talk about the total effect, which is basically the case where the direct intervention and the indirect path through M take the same A. Okay, so it's sort of saying, look, this is a sort of real life experiment where we're saying, if we intervene on A, what's going to happen? And what you can see here is that if you intervene on A, you can sort of compare different interventions. And you can see that 1600 hours versus 480 hours means a 0.1 reduction in arrests. Is this because of the direct path or indirect path? Well, we don't know yet. And we don't know yet because we've not decoupled the distribution over M from the direct intervention, right? They've got the same A. So now let's decouple them, right? So now let's say we're doing this intervention here, but we're taking the distribution that we would have under the old A. Okay? And we were hoping when we did this experiment for an interesting answer, and we didn't get one. So if you compare these two graphs, they're exactly identical. That's very sad. So basically, what that means is that for the purposes of this study, the indirect effect via employment is effectively not present. So what that means is that in fact, taking this class is what has the biggest effect on the chance of being arrested, and the indirect effect via employment, at least from the analysis that we've done, seems to be very minor. So this might not always be the case. So in other settings, it might be that indirect effects matter much more, but we didn't find it for this data set, unfortunately. But it's still a nice thing to have explored. Now we can do something even cleverer. So this is something called dynamic treatment effect. So this is a setting where we take a sequence of treatments, and each treatment can affect the covariance at future times. So this, a famous example of this is treatment for AIDS, where you give a sequence of medications, which in turn influence the patient, symptoms and so on, and then you get an outcome of how much the viral load has been reduced. And so in this case, you can do this study for a sequence of treatments and a sequence of X's, sequence of outcomes, and then you can again run experiments. Like if I intervened on this first medication or on the second medication, or I made these interventions conditioned on other things, what would happen? So I think this example here is a very interesting one, and it's one that is obviously very important in practice in epidemiology and so on. And so this is also something that you can do quite straightforwardly with the methods I've described in this course. Notationally, it's more complicated. Practically, it's not. So it's very simple to do. But yeah, this is another thing which we can explore using the tools that we've described. All right. So this ends the part of the course for the observed data. So we talked about average treatment effect, conditional average treatment effect, dynamic treatment effects, mediation effect, average treatment untreated. In the setting where A, covariates, proxy, actually proxies are coming later, are multivariate and complicated. So the next part of the lecture is going to be for unobserved confounders. I think this is actually, I'm going to stop for questions at this point, just to get some questions about the observed confounder case. And then I'm going to already start talking about the unobserved case, because the unobserved case, I think, contains a bit more material and is going to take longer. So maybe, yeah, now's a good time to come to the microphone and ask questions about the observed case. All right. So now we've done the case of everything observed. Let's make our lives a little bit more difficult. So we're going to now look at the case of unobserved confounders. So let's, I'm going to sort of remind ourselves of our setting, because we need to have this at the forefront of our mind to go ahead with this. So remember what happened when we had our observed data. We've got our x, which influences our a, which influences our y. And we have our basically probability being cured given pills, probability being cured given surgery. And then intervening is different from observing. So if we intervene on A, we get this quantity here where we've sort of flipped our ordering. So this is fine. But in computing these quantities, it's enormously important to know this, right? Without knowing this, I can't compute this quantity. So what happens if we don't see it? And the short answer is, well, you can't do anything, right? Because imagine that you're in this case where there is like an adversary who's just like controlling your patient welfare depending on medicine and is like miraculously curing patients you give no medicine to and killing patients you give medicine to. I mean, then you can't guess what's going on. So in the worst case, this X can be doing something like incredibly like pathological, like, taking the medicine and hiding it. There's all sorts of bad things that can happen. So the short answer to if you can't see X is there's nothing to be done. But the longer answer is in certain circumstances, there are things that can be done depending on the assumptions you make and what you see. So obviously you don't see X, but you see like something else. And what is that something else? Well, we're going to find out. All right. I'm going to remind us of our assumptions. So the assumptions are that the pill that I take doesn't cure you. There is no additional hidden V here, which I don't account for, though there can be hidden X, which we do account for, but the X-ray hidden V cannot occur. And then I'm never making predictions about things I don't see. So these are my ground rules. All right. Now, for everything that I'm going to talk about from now on, I'm going to make the following assumption. All functions are linear combinations of a finite dictionary of adaptive neural net features. So before I talked about infinite combinations of fixed kernel features, now I'm going to have a finite set of features, but these features are going to be adaptive and they're going to be neural nets and we're going to learn them. All right, so finite dictionaries of learned neural net features. We're going to fit these using ridge regression. Okay, surprise? Well, no, because I said there's only one algorithm for this whole course and it's ridge regression. So we're going to fit them using ridge regression. Okay, so we're doing regression from X to Y. Here are our features, right? Our neural net features. Here are our weights. And we're going to try and minimize this squared error. We're going to use this term here, which is a stabilizing term, which is going to be quite useful, which is just the sum of the squared coefficients of this linear final layer. Now, it's kind of weird that we're treating the linear final layer differently, right? Why not just have a neural net with just parameters theta, which includes gamma? That's a good question, and we're going to get to the answer of that. There are two answers. One is a simple answer, and one is a complicated answer. The simple answer I'm going to give now, the complicated answer I'm going to give later. So here is the closed form expression for gamma in terms of the features theta. Right, so this is, let's say d dimensions, my d-dimensional final layer before I take a linear combination of those features using gamma to predict my y. This is a function of cyx, which is the cross covariance between y and my features of x, and the covariance of my features of x with themselves, right? So I've got this in closed form. So, why bother getting that in closed form, right? I just do SGD on my gamma and my theta together, surely that's enough. Well, here's something interesting that we found. So one thing that we could do, rather than doing SGD on gamma and theta together, is to take this closed form solution, substitute it in here, and then backprop through Cholesky, because we're actually going to use Cholesky decomposition in order to solve for gamma. We're not going to do the inverse, in order to get theta, right? So I have two options. Option one, SGD on everything. Option two, linear final layer, backprop through Cholesky to get theta. Now, interestingly, option two seems to be much better. So here's a toy example. This is just a 4-layer fully connected sigmoid network. Here's number of epochs, training epochs, and here's mean squared error. This is what happens when you just do SGD on everything. This is what happens when you do this trick. It seems to be much better. Now, why is that? I can only give you a conjecture because I don't have a formal proof. But in a sense, what does this linear final layer do? It kind of decorrelates the features of X, and then it covariates them with Y. Like that's how linear regression makes its a prediction. Now, if you're trying to adjust theta and gamma at the same time, then you kind of have to take very small steps of gamma and theta together to sort of maintain the decorrelation effect of gamma and theta. Whereas if you just say, well, look, I know gamma in closed form, then I can take much bigger and easier steps on theta. So this is, as I say, a conjecture. I think it would be very interesting to prove that you're going to get faster convergence using this than using just SGD on everything. But we haven't done that proof. Maybe this is well known to everybody already. I don't know, but this is just something we noticed, which we think is really interesting. And so I wanted to alert everyone to it. So that is one of the reasons we're treating the linear final layer differently is it works much faster. So that's a pretty good reason. There's another reason that we're treating the linear final layer differently, which you might already be able to start to guess depending on the part one of this talk. But if not, you're going to see pretty soon why. So are there any questions about this rather weird discovery? Okay, good. So the first approach that we're going to describe in order to account for hidden confounding is something called instrumental variable regression. All right, so I'm an aircraft executive, okay? And I want to know the effect of selling my ticket price on the number of seats that I sell on my plane, okay? So, let's say that I used to be a hospital administrator, but then I killed all my patients by making them take pills. So now I've got a job in an airline, and this is the job I have. I'm going to set the ticket price in order to sell as many seats as I can. Now, I observe historically the following plot. Here is the ticket price. Here is the number of seats that I've sold. And I've learned linear regression, so I do it. And then I say, well, I know how to sell lots of tickets. I'm going to make my price go up as much as I can, because obviously, using linear regression, that is the way to sell more tickets. So what have I done wrong? What I've done wrong is that I've neglected a hidden variable X, which is how badly do people want to travel? Okay, so let's say that I've got my price of tickets, I've got my number of seats sold, but then I've got this hidden X, which is determining how badly people want to travel. And for the purpose of this illustration, I'm going to give this distribution 3 modes. So this is how badly do people want to travel in the middle of winter to Okinawa. Here's how badly do people want to travel in summer. And then here's how badly do people want to travel when there's a machine learning summer school and everyone wants to come here. So obviously you've got sort of 3 levels of demand, low, medium, and high. Okay, so this is my X, but let's say I'm an airline executive. I don't know what a machine learning summer school is. And so I just know that there are these different levels of demand, but I don't know when or why. So conditioned on desire for travel, right, A is influenced, okay? So basically the price at which I sell my tickets is going to be desire for travel plus some normally distributed random variable Z, which I'm going to come back to shortly. But for now, let's just call Z a normal variable. So what's interesting is that the price is going to go up when desire for travel is high. So remember how airlines price their seats, right? As the plane fills up, the seats get more expensive. So if desire for travel goes up, lots of people want to fly, lots of seats get filled, the prices are high. Okay, so desire for travel high means that price is high. Desire for travel is low, well, the plane is empty, price is low, you're going to buy a ticket for like $10. Now, what about seats sold? Well, I'm going to have seats sold is going to reduce as number of price, as price goes up. Seats get very expensive. At some point, I'm not going to sell them. But then I've got also this influence of desire for travel, right? Because if you really want to go to the MLSS, even if the plane is very expensive, you're still going to buy a seat. So basically, this is going to be the equation that governs the number of seats sold as a function of price. So price goes up, seats sold go down, and desire for travel. And so these 2 equations here are what describe the graph that I saw on the previous slide. And you can kind of see that, right? low desire for travel, medium desire for travel, high desire for travel. Okay. Now, what is my average causal effect? So this would be, what is the effect of intervening? What is the effect of basically saying, over my population, on average, low, medium, high, what happens when I intervene to set the ticket price at some value? And so obviously, this is something I'm interested in as an airline executive, like what happens if I set my price to this level, to that level, to that level, on average over my population? And so here is the y given a and x, right? E of y given a and x, and I'm going to average that over x, right? I'm going to average that over my hidden desire for travel, and then I'm going to get 10 minus a. Great, I know now that if I increase my price, I'm going to sell fewer tickets. So now you know that as well. But bad news, I don't see x, right? So everything that I taught you in the first half of the course is useless for this problem. So what do I do? I said I'd come back to z, so I'm coming back to z right now. So z is in fact the price of gasoline. So z is a variable that influences the price. So obviously if gasoline gets more expensive, I have to increase my price. I have no choice, okay? But z is independent of whether there's an amazing MLSS in Okinawa. So this z variable influences a and is independent of x, okay? And in particular, the conditional mean of x given z is 0. So z is kind of a way that nature forces you to make experiments. Like, I can't tell my airline executive, hey, why don't you just set your prices at random and see what happens? I mean, if an airline executive would do that, that would be fantastic because I'd break the link from x to a, and then I'd be able to compute the average causal effect perfectly. But like no airline executive is going to set their prices at random. But if gasoline price changes, well, that forces my airline executive to adjust their prices. They have no choice. And so this is sort of nature's experiment. It's nature's way of basically decoupling the variation of a from x. And in using that decoupling, I am able to determine the effect, this sort of causal effect of a, which is my ticket price, on y, which is the number of seats I sell. So in particular, I take this equation, I condition both sides on z, which is the price of gasoline. I notice that this is 0, and then suddenly I recover my average causal effect relation. So basically, I've got this sort of 10 minus a relation again. So conditioning on the price of gasoline allows me to recover the effect of intervening on price on the number of seats that I sell. So this z, I'm going to call an instrumental variable, and what I've just shown you is an instance of instrumental variable regression. So just to give you one more illustration of this, I'm going to give you just a very simple example in the case where all of my variables are linearly related. So let's say that I'm predicting y from a. I've got my x, which is my hidden variable, and I'm going to say that x and a are dependent, right? So this is a scenario which we've got here, that x and a are coupled. So this covariance between features of a, I'm going to say neural net features of a and x, is not 0. All right. My average causal effect, I showed that on the previous slide. So this is the relation between y, a, and x. So my y is a linear combination of features of a plus x in our modeling scenario here. The mean of x is 0. I'm going to assume that, right? My average causal effect is going to be, well, just this weighted sum of features of a, because I'm averaging over my x is additive, that's going to be 0. I need to therefore recover this gamma here, right? If I recovered the gamma, then my average causal effect would be very simple. It would be just a linear combination of my features of a, right? But how do I recover my gamma? Well, I could recover my gamma just by minimizing the squared loss, right? That's a pretty obvious thing to do. So here is my squared loss. I'm predicting y from gamma transpose a, and I've got x. But crucially, and this is where I'm in a lot of trouble, my features of a and x are correlated, right? This covariance here is not 0. All right? And because this covariance here is not 0, when I solve this and minimize, right, this is a function, it's just least squares regression again, of the covariance between a and y, but also the covariance between a and x, okay? So if I saw x, I could recover gamma and I'd be done. But I don't, so I can't. This is why we have to use instrumental variable regression in order to get rid of this x here by conditioning on z, in order to solve for gamma and to solve this problem. So this is like a pretty straightforward case where everything is linear, notwithstanding that I'm using nonlinear features of A. And I'm sort of revealing to you from this slide the fact that this covariance between A and X becomes important when it's not zero. So when this confounding variable here, when this confounding variable here and this A here are coupled in complicated ways. All right. So I think, so this is instrumental variable regression. I will also emphasize that in 2021, these three individuals received a Nobel Prize for their work on IV. And in particular, they were awarded this prize basically by finding good natural experiments. And so this is, I think, one of the merits of IV regression is if you can find a good instrument, which is sort of something that influences your treatment, your A, and is independent of this hidden confounding, then you can do like really powerful and interesting natural experiments from observed data, which allows you then to sort of explore lots of phenomena in the world and figure out like what would happen if we sort of intervened on various things in econometrics, in epidemiology, and in many other disciplines. So the tool is actually very powerful and very well established. So I think this is actually a good time to pause for questions, and we're going to continue with IV after the break.
Let's thank Arthur first.
All right. In the end of the previous lecture, we set up a little bit of a mystery, which is this instrumental variable regression. We're now going to resolve that mystery and show you how to do instrumental variable regression when our treatment is high dimensional, where our instrument might be high dimensional, using neural networks. Okay, so let's begin by just a quick recap of where we got to at the end of the last lecture. So remember that we had this x, which is a hidden variable, and this is the demand for travel. We have A, which is price of tickets, and we have Y, which is number of seats sold. And our goal was to find out the effect of price of tickets on number of seats sold. Now, remember that because we've got this confounding effect of demand for travel, using observational data can give us a rather, shall we say, unfortunate effect, which is that we get this sort of false sense that if you increase ticket price, then you increase number of seats. But this is just because when there's very high demand for travel, you sell lots of tickets at a very high price. And the way that we are aiming to resolve this is basically by conditioning on an instrument, which is a variable that affects the price of the tickets, but is independent of the demand for travel. And in the example that we gave, this was the price of gasoline. So price of gasoline causes you to increase your price of tickets because you have to increase the price because gasoline is more expensive. But the price of gasoline is independent of whether there's a really exciting machine learning summer school in Okinawa. So this is an instance where you have a valid instrument. In this case, basically, we can recover the fact that increasing ticket prices reduces the number of seats sold by conditioning this equation here on x. So if I condition, on z. Okay, so I condition y on z, I condition a on z, and I condition x on z. This is 0, and then I recover this fact that as I increase my price, I reduce the number of seats that I sell. So this is sort of using this gasoline variable as a sort of natural experiment, as a way of forcing you to adjust your ticket prices in a way that's independent of whether there's an exciting conference going on in Okinawa or machine learning summer school. Right. So this was the principle that we arrived at the start of the last lecture. So now let's look at this in a general setting, and then let's explain how it is that we can do instrumental variable regression when we're using neural net features of all of our variables. So this allows us to consider the case where all our variables might be quite high dimensional and complicated. In general, we have the following variable names. We have an unobserved confounder, we have a treatment, we have an outcome, all right, and we have an instrument. And we're going to make some assumptions, right? So one assumption is that the instrument has, the hidden confounder has 0 mean, and it has a 0 mean condition on z. So we need to have it have 0 mean condition on z in order that conditioning on z gets rid of it, right? We need that Z is connected to A, right? If Z is not, if our gasoline price wasn't forcing us to adjust our ticket price, it wouldn't be a natural experiment anymore. Now, this condition is kind of complicated to parse. What it means is that Y is independent of Z given A for a graph where we've broken the incoming edges, all right? That's a pretty messy kind of condition to understand, but what it means is something rather simple and rather obvious, which is that I'm not allowed to have, let's say, a V here, which is influencing both of these things, right? Then, if that were the case, then my reasoning would break down. So that's what I'm excluding by this third condition here. All right. And then I have a fourth condition, and the most important thing about this fourth condition, I've got, Y as a neural net, sum of neural net features of A. That's my modeling assumption. And I've also assumed that my hidden confounder is additive. So that means that, the relation between Y and X can only sort of be shifted up and down by X, right? That's the nature of the confounding that I'm allowing. I'm allowing this X to be added to my gamma transpose features of A, which is to say it sort of shifts it up and down, but it can't have any more complicated confounding effect than that. And that's a pretty restrictive assumption, but it's an assumption we have to make because we're going to get rid of X by conditioning on Z, and we wouldn't be able to do that if X had a more complicated effect on Y. So later on, we're going to consider a case where the confounding can have a more complicated effect on Y, but you can't do that with instrumental variable regression. You have to use something else. All right. So those are the assumptions that we're making. So that's IV. Now remember that our average causal effect, which we've seen many times now, is I take my conditional mean of Y given X and A, I average it over X, and in this case, if I do that, I just get gamma transpose phi of A. So gamma transpose neural net features of A. Why is that? Well, remember, this mean is 0, right? So when I average over X, I just get rid of that term. The term is additive, and that's it, right? So this is the effect that I'm going to try and recover by doing instrumental variable regression. Okay, and this is what I wish I could do, but I don't see X, so I'm not allowed to do that. But what I can do is this, right? I condition both sides of the equation on Z. So I've got this equation here. I condition both sides of this equation here on Z. So I get Y given Z, I get X given Z, I get this thing, features of A given Z. This goes away because I've made that assumption. And what I'm left with is the relation that I'm after, right? And in particular, I'm going to recover this gamma, which will allow me to compute my average causal effect. And I'm also going to get my neural net features as part of this training process. So this is the problem that I'm tasked with solving. And once I do that, I will then have the correct effect of A on Y. If I intervene on A, I'll be able to get my average causal effect. Right. So we can do this in two ways. We can do this using kernel features. We can do this using adaptive neural net features. I'm going to use adaptive neural net features for the rest of the talk. So from now on, I'm only going to be using adaptive neural net features. The code for both the kernel and the neural net features is given in this link here. So please, obviously, download it. Both kernel and neural IV are a little bit more complicated to implement than the simple average treatment effect and conditional average treatment effect methods that I talked about earlier. So in this case, I really urge you to use the code and to download that if you want to try these methods out. Right. So what loss are we going to minimize in order to do instrumental variable regression? Well, I said in this entire course, there is only one method, which is ridge regression. So we have to use ridge regression. Here it is, okay? So I'm going to use ridge regression to map from the conditional feature mean of A given Z to Y. And I'm going to learn both my coefficients here, my linear coefficients, and my neural net features. So this time I'm going to learn both, right? I'm adapting my linear coefficients and I'm adapting my neural net features. So you might already be a little bit worried because normally when I do neural net regression, right, I've just got a neural net function here, and then I've got my Y that I'm trying to learn, and I tune my neural net parameters. But here I've got a conditional mean of my neural net features. So I'm doing something a little bit funny to the inputs of this regression here, which is that I'm taking the conditional mean of these features before I apply my linear final layer. So this is already this should already make you a little bit worried. Okay, now I need this conditional feature mean of features of A given Z. And how do I do it? Well, I do it exactly as I did for the conditional average treatment effect example that I described earlier, which is to say that I have some neural net features of Z. I apply to them a smooth operator, in this case, just a matrix F. And when I apply this matrix F to these features of Z, I'm going to get my estimate of the conditional mean of the features of A given Z, right? It's a matrix, a linear final layer is a matrix because I'm mapping to a set of features. So obviously, the number of features that I have is more than one, and therefore I need a matrix rather than a vector as my linear final layer. And there's only one algorithm, ridge regression, so I learn this matrix using ridge regression. Okay, so here is my challenge. How do I learn for my primary regression, for my green regression? How do I learn the neural net parameters theta? So you might remember I talked about backprop through Cholesky, right? So I'm going to get this in closed form and then backprop through Cholesky to get this. But here's a problem, right? So that might be an idea, like I'm going to get this in closed form, but what's kind of problematic about that is that I don't have just the features of theta here. I have the conditional mean of the features of theta, right? So, well, what if I had the conditional mean of features of theta from my stage 1 regression, which is to say this stage of regression, right? Well, the trouble is that to get the features of theta from the stage 1 regression, I need to learn F. To learn F, I need to get phi of A. To get phi of A, I need to know theta. So it seems that to solve this problem, I need to solve that problem. To solve this problem, I need to solve that problem, and round we go. So we seem to have got ourselves into a bit of a problem. How do we resolve this issue? It turns out that the linear final layers are going to be the key to resolving our problem. So I said in the previous lecture that the linear final layers have both a simple implication and a complicated implication. So we're now getting to the complicated implication, which is that the linear final layers allow us to link together this regression and this regression in a way that allows us to adapt both of them simultaneously. And we're going to now see how that works. Okay, so my goal is I solve this regression to get my conditional features of A given Z, and then I take those conditional means of A given Z and I plug that into my Y. But my challenge is to adapt these neural net features here, which appear both as the input of this regression and as the output of that regression. That is my challenge. And as always, please, if there are any questions, don't hesitate to stop me. All right, so what am I going to do? Let's just get rid of this part and focus first on the stage 1 regression, okay? So here is our stage 1 regression, right? I'm going to try and find a matrix which maps these neural net features in order to get an estimate of the conditional mean of features of A given Z. And let's just assume right now that these features are fixed, right? So I'm going to use ridge regression to do that. I'm going to use ridge regression to map from features of Z to features of A. And I've got this linear final layer, this matrix F, which is what I'm going to learn, right? And remember that this linear final layer I have in closed form. It's just ridge regression, right? We've seen this a million times. So what is this linear final layer? Well, it's the cross covariance between A and Z, and this covariance between Z and itself, right? So cross covariance between features of A and features of Z, and covariance between features of Z and features of Z. So I can plug this in, this F in, to my regression function, and I can backprop through Cholesky, right, in order to find my zeta features, which is to say the features of my Z. All right, so I've got this in closed form explicitly as a function of theta and zeta, right? So I've kept the solution explicitly in terms of those features. I've plugged that in here. I've done backprop through Cholesky. That has allowed me to get my zeta features. Now, the F is also a function of theta. Couldn't I also backprop through Cholesky to minimize with respect to theta? The answer is no, right? Why is the answer no? Think of what this feature means. This is the feature of the output of my regression, right? Now, what's a really easy target to regress to? What about the vector of zeros? That's an easy target. So if I was allowed to change my theta in this regression function here, it's like marking my own homework. It's like, oh yeah, I got the question right. So what I would do, and this is actually what happens in practice because we tried it, is that if I adjusted this regression function here with respect to theta, including F, I would just learn a really easy vector to regress to. bad news, I need this in my primary regression, right? I need this in order to predict y. So this is a perfectly good vector if my question was only to regress to features of A that I choose, but it's not much good if I want to then use that downstream in instrumental variable regression. All right, I hope that's clear, right? So I can't backprop through Cholesky to get theta from this stage 1 regression, because if I did, I'm cheating. I'm basically giving myself a really easy problem to solve and then solving it, but it's useless. All right, but it's still interesting what we've achieved here. What we've achieved is to get this f explicitly as a function of theta, and that is useful. We're going to use that. Okay, and we've also been able to optimize over our zetas, so that's also useful. So we've done 2 useful things, but we have to make sure we don't do something silly. Yep. Yes, so absolutely. So I've sort of said for the moment we're fixing theta, and we've adapted zeta for that theta. Shortly, we're going to come to the problem of like the zeta theta interaction. So I think you've discovered already something that is going to arise quite shortly. Yeah. So this is of course the correct zeta for the current theta. Yeah. Any other questions? All right, so let's take this f and see what we can do with it. Okay, here's our regression, and I've got my gamma transpose and then conditional mean of features of A given Z. Well, we've learned in stage 1 how to get these conditional features of A given Z, right? It's using this matrix here, which is an explicit function of theta and zeta, acting on these neural net functions of zeta. And we've optimized zeta in stage 1 for the given value of theta that we've now got. And we've now plugged this into stage 2. So we now know how to get gamma in closed form as a function of f and these features here, right? So gamma in closed form is just basically, the cross covariance between features of y and A given Z, and the covariance features of A given Z. So this is the covariance of features of A given Z. This is the cross covariance of features of y and A given Z. All right, so it's just ridge regression once more. But what you can see here is that we've kept explicit the dependence on theta here. Okay, so this gamma function is dependent on theta, and that includes the way that the f changes with theta. All right, so we can plug this in, and we can backprop through Cholesky, and then we can use that to adapt theta. And this is allowed because the theta here is the input. So backpropping through Cholesky for stage 2 is not cheating. It's just adapting my input features to make a good prediction. And so this is allowed. And what's key in this reasoning is that this f remains optimal with respect to whatever our current theta is. So what that means is that my conditional mean of my features of theta given z remains a correct conditional mean, albeit with a fixed set of neural net features on z. Okay, so basically, as I'm adjusting theta, I'm still predicting the correct conditional mean of my A given my Z. And the reason is because of this F. But as was alluded to in the question a bit earlier, the optimal zeta does change when theta changes. All right, so my linear final layer is adapting automatically, and that's sort of what glues the 2 layers together. And this is what's so important about using these linear final layers. However, of course, the best zeta might change, right? The best input features might change. And so what we're going to do is we're going to alternate. We're going to optimize theta in stage 2. We're going to optimize zeta in stage 1. And we're going to alternate these 2 optimizations until convergence. So lucky for us, this is a min-min problem, not a min-max problem. So it's not an unstable problem like a GAN. But nonetheless, what we're doing is we're alternating 2 neural nets. And we do that until we get convergence, and that's our solution. So are there any questions about that before I go on? Yeah, so this is reasonably unusual in the sense that I've got basically 2 neural nets working together in order to solve this problem. The first neural net gets my conditional means of my features that are the inputs to my second neural net. And it's kind of interesting that basically like this is solving a problem that needs to be solved in order for this problem to work. And so these neural nets are sort of collaborating in order to solve the IV problem together. Great. So where do we apply IV? So I mentioned at the end of the last lecture that one domain in which instrumental variable regression is applicable is in reinforcement learning. And the reason is because there is a reinforcement learning that is, let's say up to some notation, very, very similar to IV. So basically, I'm going to address the problem of policy evaluation. In particular, my goal is to estimate this Q function here, which is the expectation of the discounted future rewards starting from a particular state and a particular action. So I start at some state, I take some action, then I follow a policy for subsequent states in action up to infinity, a policy being my choice of subsequent action given my state, and then I get a sequence of rewards. And I want to know under that policy, like, how good is my policy? What is my expected future discounted reward given that policy? Now, in order to obtain Q, the Q satisfies a self-consistency equation called a Bellman equation. What does that say? Well, it says, well, if I start at SA and I take a single step forward according to my policy, so I get S prime is A prime given SA, right? This is my discounted reward of a single step. This is the actual reward I see, which is a random variable. And this equation here, this expression here should match this reward here, right? So basically, if I compute my Q value at one time step forward minus my Q value at the current SA, then that better be consistent with my reward, because that's what the Q value does. Okay, so if my Q function satisfies this self-consistency equation in expectation over S, A, and R, then it's the correct Q function for that problem. All right, so what is the loss that I'm trying to compute? Well, this is my R, so my Y is my R, that's the reward. And then I'm taking the conditional mean of F given Z. Well, what is Z? Z is my current state in action. And then F is my difference in my Q functions. So you can kind of see now how it maps onto an IV problem. I've got the expectation of some function given Z, and I've got a Y that I'm trying to compute, and I'm trying to find an F that satisfies that. Now, it's not quite the same because I've got here my F as a difference in Qs, so the parameterization is a bit different, and my Z has some variables in common with my X. So again, like there's a little bit of fine print going on here, but at a high level, you can see how this looks like an IV problem. And in this case, satisfies the IV requirements. So once again, for details on the application of deep IV to reinforcement learning, we've got some nice experiments here and some code, so you can try this out. So here is an example for the mountain car, but we've tried this actually on a whole bunch of different benchmarks. So we tried this on, catch, mountain car, cart pole swing, cheetah run, humanoid run, walker walk. So we've tried this on a whole bunch of different domains from a number of different reinforcement learning suites. And what we're seeing is actually we're getting pretty good performance with this deep feature IV. So with instrumental variable regression using deep neural net features. And in particular, this is our method in red here. So you can sort of see it. And we're doing, basically on par with fitted Q iteration, quite a bit better than deep GMM, which is a generalized method of moments. So we're actually, in practice, this method does work pretty well on IV problems. So it's a pretty effective method. So obviously, if you've got problems of this nature, I encourage you to use some of the code that we've made available. All right, are there any more questions about IV before I go on? No questions. Okay, great. So let's now look at another approach to learning when we've got hidden confounding or hidden covariance. So IV had, a reasonably strong limitation. So let's just go back a couple of slides. Right, this assumption here is a pretty strong one, right? We're requiring that the hidden confounding is additive. So that's fine. If we expect that this hidden confounding is sort of shifting things up and down, like the number of seats sold on a plane, if demand is high, it shifts up, if demand is low, it shifts down, But what if the influence of x on y isn't just this simple, plus, or minus x? What if it's something a bit more complicated? Then instrumental variable regression is absolutely no good to us at all. Because how do we deal with this hidden confounding? Well, we have to use this, right? We have to use that it's additive and that it's conditional mean given the instrument is 0. So this is a strong requirement. Can we think of a way to correct for this hidden confounding and estimate causal effects when the influence of x on y is more complicated? So this is what I'm going to be dealing with in the rest of the talk. And this is a much more modern method. It's an approach that was actually introduced in the econometrics literature in 2018, and that we've recently used kernel methods and neural net methods in order to implement. So this is called proxy causal learning. All right. So first of all, I'm going to return to the example that we started the talk with in order to illustrate a challenge that arises. Okay, so we know how to estimate the average causal effect when we observe x. But what if the doctors observe x, right, the severity of the disease, they decide on a treatment, you then get an outcome. What if the doctors just write down some summary information about what they see? So the doctors see the patient, they notice a lot of things, but let's say that all that they write down is whether the patient has a fever or not. So the fever is a pretty good indication of severity. I'm going to say that the probability of fever given the disease is mild is 0.2, probability of fever given disease is severe is 0.8. So the W isn't exactly the same as looking at X, but it's a pretty good proxy for X, right? It's a pretty good indication of the severity of the disease, but it's not perfect. Okay, it's a little bit noisy. So what you might wonder then is, well, what if I treated W as if it were X when I'm estimating my average treatment effect or my average causal effect, right? So remember that the classic average treatment effect, I was saying, well, I've got my E of Y given A and X, and I'm going to sum that over X, right? Px. And now what I'm doing is I'm saying, well, W it's not X, but it's close enough, right? How bad can it be? It's a slightly noisy version of X. So let's add, let's act as if W were X and see what happens. So the bad news is that if you do that, you're getting answers that are quite far from the answers that you should have got, even though W is not too noisy of a view of X. So here, if I use W as if it were X, then the chance of being cured with the intervention pills, I'm getting 0.8. I should have got 0.64. That's pretty bad. Surgery, I got 0.73. I should have got 0.75. So what's especially bad about this is I've actually got the wrong order here. So under the intervention of pills, I should have got a worse outcome than under the intervention of surgery, but I'm actually getting the reverse of that when I use W as if it were X. So that's actually pretty bad. I'm going to kill a bunch of patients through having made this error. And I will also emphasize that these parameters here, I didn't sort of do some exhaustive search over my model parameters in order to get these answers. So it's not some sort of edge case. This is actually, quite a foreseeable outcome. So the question is, what do you do? And the short answer is that without observing X at some point in training, it's impossible to find the average causal effect with the information that I've shown in this graph. So this is from a paper by Judea Pearl in 2010. So he was sort of looking at using a noisy proxy of X in order to identify the causal effect. And he said, well, if you see X in training, you can do it. But if you don't, then you can't. So bad news. All right. So I've just told you that the problem is impossible. So now let's try to solve it. We're obviously going to need more information than this noisy W. How much information do we need? And where should we see that information? So that's what we're going to do next. All right. So what we're going to use are variables called proxy variables in order to solve this problem. They're also called negative controls. Proxy, I'm using that word deliberately because in a sense, W has been a proxy for X. And so this is sort of to give you an idea of what a proxy variable means. It means that it's not X, but it's something to do with X. All right. So there are particular applications of the methods that I'm going to describe. One is in inference or inferring causal effects in a circumstance where the data that we gather is subject to privacy constraints. So let's say that I'm trying to find a better way of prioritizing important email, but I'm not allowed to read your email, right? I'm only allowed to read an anonymized version of your email, but I'm still trying to make recommendations of what emails are important and what are less important. Another instance might be data gathering constraints. So let's say I've got an edge device, I'm sending data back to the mothership, but I can't send back all of the data that I see. So I'm going to send back some sort of compressed summary of that data. A final setting where these things are relevant is where X is intrinsically unknowable. So let's say that X is my state of mind, right? So there's no way that I can communicate perfectly my state of mind to the world, but I might have indirect indications of that, through my actions or through my interactions with other things. So this is a circumstance where the methods that I'm going to describe are going to be relevant. All right. And as always, the merit of the method that I'm going to describe here are that it's able to deal with data that are very high dimensional, because we're going to learn neural net features of all of our stuff. So the proxy variables can be high dimensional, complicated. My treatments can be very complicated. They can be text, they can be images. And I'm going to learn neural net features of everything in order to do the inference. Okay. Now, one thing that you might wonder just at the start of the talk is, is Arthur going to try to find a method to learn these hidden covariates? Am I going to do something like an autoencoder or nonlinear ICA or one of these methods that explicitly reconstructs X from everything that I see? And the answer is no. So a message for the remainder of this talk is, don't meet your heroes, don't learn your latents, okay? The method that I'm going to describe is not going to require you to learn, to model, to find your hidden variables. They need to be there, and you shouldn't look at them. So that's a message of this remainder of the talk. And it's a bit like IV, right? I never tried to model my hidden X in IV. I'm not going to try to model my hidden X in this setting either. It's good that it's there. It needs to be there, but I shouldn't model it. All right. Okay, so what are proxy variables? Where should they be? What should they connect to? How are they useful? So I mentioned the problem of prioritizing important emails. So this is the example that I'm going to begin with here. So let's say X is a view of the contents of my inbox. Okay, and that's going to contain all my emails, no encryption, no anonymization, just a clean text. And then me as a user, I'm going to click on the important emails first and deal with them. And then I'm going to get some good outcome, which is some sort of efficient dealing of the emails of my inbox. So, I'm going to minimize the time I spend dealing with emails. All right. So let's say now that I want to learn the effect of intervention, so the effect of some action in this setting, but I don't get to see X. All right. So maybe what I get to see is an anonymized version of my inbox. So I don't see the clean text of the emails, but I see anonymized emails. So this is W. W is a proxy. Okay, this is the anonymized contents of my inbox before I start taking action, before I start clicking on important emails and answering them. Now, I've already said that using W as if it were X does not allow me to discover the causal effect of some action A, right? The effect of some intervention A in my setting. So, using W on its own, I've already demonstrated to you this is not sufficient. But what if we saw something else? What if we also saw the contents of the noisy inbox after the user action? All right, so this is the noisy inbox before the user action. This is the noisy inbox after the user action. Okay, so I've got my inbox X. I make some intervention on it, so it goes to X prime. I then noise it up and I get Z. So obviously the Z depends on the actions that I took and on the state of the inbox before I took those actions. And now I have two pieces of noisy information. I have the Z, which is the anonymized inbox after my actions, and I have the W, which is the anonymized inbox before my actions. And using the change in this anonymized data before and after my actions, it turns out is sufficient to get my average causal effect. Okay, so that means that if I do some, if I want to know the effect of some intervention A, I can determine the effect of some intervention A after seeing only, the Z, A, X, and Y, but I don't have to see X. Sorry, the Z, the W, the A, and the Y, but I don't have to see X. So this is, I think, quite remarkable. However, I don't think this is a very useful problem to solve in this context, right? So think a little bit about what it is that we've done here, right? We've looked at the average causal effect of some action. So what this is sort of saying is that on average, over my user inboxes, what is the effect of doing something completely independent of the contents of my inbox, right? Let's say my action A is to highlight the first mail in my inbox. On average over all my inboxes, is that going to be a good thing or not? I mean, so that's a very boring question to answer, right? Because like that's what you would really want to be doing is to design a policy, right? A new policy to highlight important emails to help your users. And in fact, this is what we can do using the tools that I'm going to describe. So this might be a much more interesting thing. So this is the average causal effect of a policy of choosing some actions conditioned on X. So basically, like I have my edge device, I've got my user emails. I have now a policy of highlighting important emails given the contents of the user inbox, but I'm evaluating the effectiveness of this policy using all of the aggregated and anonymized emails of all my other users. So this is what I'm going to do here. I'm going to stick in this presentation with this here, so the average causal effect, because this is less notationally burdensome. But I want to emphasize that you can answer much more interesting questions like this question using the tools that I'm going to develop today. So I'll describe how to do this, but this is what we're also able to do using these tools. Any questions about this email example before I go on? All right, so this is a case where proxy variables are useful for recovering causal effects with hidden information where the information is hidden due to privacy constraints. I want to also give a second example. I just want to give a few examples of these proxy methods so that you all get like a feel for where they're useful and what they do. So let's look at another example, which is a fitness tracking example. All right. So let's say that X is the state of fitness. So this is like somebody's body, and this is the intrinsic state of fitness of an individual. Now, unless you're an Olympic athlete, you're not going to get like a VO2 max reading by sitting on a treadmill with an oxygen mask on your face with a blood pressure cuff and all of this stuff, right? So we're not going to get a very good view of the fitness level of the individual. What we're probably going to get is W, which is like I've got a Fitbit or an Apple Watch, and it's going to give a reasonably good guess of the various resting heart rate, VO2 max, and whatnot, but it's not going to give a very precise view of those things. I mean, that's a much more expensive thing to do, right? And now I've got some modes of exercise that I can do. So in this case, I can do cycling or I can do swimming, and then I have an outcome that I'm trying to achieve with my fitness app, which is maybe like improving my time in running a marathon or something of that nature, all right? But once again, like it's of the nature of the problem that I do not have a very good view of the fitness of the person who's using that app, because I just can't afford to put them in a lab and take all those readings. But what I have is a noisy view of their fitness before this exercise program, and I have a noisy view of their fitness after the exercise program. And using this change in the noisy views, I'm able to determine the effect of intervening on my population. So I can say, look, I've gathered all this data from my Fitbits, and now I can start making recommendations to improve people's fitness based on the noisy data that I've gathered. So, if somebody wants to run a marathon, then maybe one mode of exercise is a bit better than another mode, and I can make these recommendations. So again, like, it's not possible to have access to X just physically, but it is possible to use the noisy views of that X in order to estimate causal effects. So in order to estimate the intervention A and to make recommendations to our users in future based on this past noisy data that we've gathered. Okay. Hopefully that's clear, but again, like any questions, please let me know. Great. Okay, so these are examples. So now it seems almost miraculous, right? Like, how is it that I use noisy information of W, noisy information of X, like W and Z, in order to recover the effect of A under X? It seems a little bit too good to be true. Obviously, there are going to be assumptions. And so now we're going to start working through those assumptions and finding out what it is that we need to assume in order for what I've just said to work. So here is the general setting. I've got X, which is an unobserved piece of information. I've got W, which can influence Y and is connected to X, but has to be bottlenecked by X from Z and A, okay? So W, I'm going to call the outcome proxy. So this might be the state of my inbox before, or the noisy state of my inbox before I take any action, or it might be my fitness levels before I take an exercise program. And then I've got my Z here, which again is connected to X. Z might be my noisy fitness levels after my exercise program. It might be my noisy inbox after I've taken my action. So Z is, yeah, the noisy, yep. Mm-hmm. That is, yeah, very good point, right? W does not directly influence A, right? So the actions that I take as a user, I've got X, right? Me, myself, I know how tired I am, how fit I am. And so the exercise that I do, I have access to my state of physical health, right? But what does Apple see? Apple just sees this. Apple just sees whatever my watch outputs. So this is a very important distinction. Knowing X, I would not need W, right? The actions that have been recorded historically have been recorded by users who have access to X, right? If I am looking at my email, I'm not going to look at anonymized email to answer email. I'm going to look at my email, right? So the users that I'm recording from have access to X. It's just that Apple or Google are not allowed to see X. They're only allowed to see W, or in the case of fitness, they're only allowed to see that. Yeah. No, but that's a very important point, and thank you for raising it. Yeah. Any other questions? Great. Yeah, so I've got my W, and as we've emphasized here, W is not directly connected to A because the data that we've gathered, X informs A, right? Now, Z here is allowed to be connected to A because it could be the consequence of A, right? Or some noisy view of the consequence of A. I've made these arrows a little bit more general. So in particular, I don't take any position about the relation between X and W. So it may be that X causes W, maybe W causes X, maybe there's a hidden common cause, I don't know, I don't care. And likewise, in the examples that I gave, A causes Z, but it needn't be the case, right? So I can be a little bit more general than the examples that I gave, but the examples that I gave are, to my mind, the most interesting examples of this setting, which is why I sort of emphasize them. But I can solve more general settings as well using this. So what assumptions does this graph encode? It encodes two assumptions, right? W is bottlenecked from ZA by X, right? So conditioned on X, W is independent of Z and A. And this makes sense. If I know my clean inbox, then the noisy inbox is independent of the inbox at a future time, given the clean inbox, right? That's pretty obvious. Likewise, Y is bottlenecked from Z given X and A, right? So my outcome is bottlenecked from Z given the state of my clean inbox and the action that I've taken, right? Again, it's intuitive. These two assumptions, which are encoded by this graph, are the core of what makes it possible to recover the causal effect of A under this unseen X. So I've color-coded them. So I've got assumption orange and assumption purple. Hopefully that's helpful for us in keeping track of them in future because they're going to be used pretty much from now until the end of the talk. Okay. So using these two assumptions, I'm now going to demonstrate to you that it's possible to recover the average causal effect of A on Y with hidden X. And it's going to be just a very small amount of quite simple algebra. Okay, so first of all, what would be the average causal effect if I could see X, right? You've seen this many times. I'm just going to remind us once again. So here is the average causal effect, which is probability of Y given X and A, marginalized over X, right? And in this example, I'm going to say that X is categorical. X can only take one of the X values, so this is a sum. I'm going to now express this in slightly more succinct notation, which is as a matrix for each A. I've got a matrix, a dy by dx matrix of probabilities of Y given X and that A, marginalized over this vector, right? This is P of X, a vector, okay? So this is a matrix vector product. So I'm doing that in order to avoid having my slides cluttered with summations, but hopefully you're all clear about this matrix vector product being a marginalization. Right. Now, Bad news, I don't have X, so I need to get rid of it. So my aim for the next few slides is to get rid of the blue. If my equations have no blue in them, I win. Now, let's say that for each A, we could solve the following equation, right? What does this equation do? It maps P of W given X with this matrix H to Py given X and A. Now, obviously, I'm going to need a different matrix for each A. This matrix is going to be a dy by dw matrix, so the dimensions work out. So let's say that I could solve that. Let's say that I could obtain this matrix. What would it mean if I could obtain this matrix? Well, let's say this is my average causal effect. So this is Py given Xa marginalized over X, as we saw from the previous slide. Now I'm going to substitute in the equation here, there, right? So this is H Pw given X Px. Now, Pw given X Px, that is marginalizing over X. So what have we done? We now have an expression for the average causal effect where we marginalize over W. So remember before I said, well, you can't treat W as if it were X. But I can treat W as if it were X if I use H here rather than Py given W and A, right? So this H matrix here allows me to marginalize by just marginalizing over W. So that's great, but I would need to solve this system of equations here. And I can't do that because I don't have X. So like I've said, if I could do something that I can't, then I could solve this system of equations. Well, that's great, but I can't. So yeah, I'm stuck. But this is still an interesting idea. Okay, so what do we do about this? How do we get rid of the blue? So this is from the last slide. This is what I said, if we could solve this, then we can get the average causal effect without any blue. So Py given Xa, Hwa, Pw given X. What I'm going to do now is to project this system of equations onto a matrix. What is that matrix going to be? That matrix is going to be Px given Za. And at this point, we're going to start using the orange and the purple assumptions. So let's first look at assumption orange, right? W is independent of Za given X. Well, if that's the case, then doing this amounts to marginalizing over X, and that gives me P of W given Za. Great, so here I've eliminated the blue. Now I use assumption purple, right? Assumption purple says that Y is bottlenecked from Z given Ax. That being the case, when I do this product, I marginalize over X for a given A, and I get Py given Za. Again, no blue. So now let's substitute orange here and purple here, and now we're done, right? Py given Za is Hpw given Za. So now I have a system of equations purely in terms of quantities that I observed. There is no blue. We have to be a little careful here. So we have implicitly made some assumptions, and I want to sort of describe those assumptions now. So in particular, when we do this projection, what if dz were of lower dimension than dx, right? Then when we did this projection, we'd lose some subspace of our system of equations. So we need to make sure that the dimension of z is greater than or equal to the dimension of x, and that the rank of this matrix is at least dx. Otherwise, this projection is going to lose us some number of equations, and then we won't have enough equations for the number of unknowns that we have here. Likewise, Pw given x. Well, I'd better make sure that dw is of dimension greater than or equal to dx, and that the rank of this thing is of at least dx, or we're not going to have enough equations for the number of unknowns that we are trying to solve for. So this is sort of saying that, w can have dimension which might be higher than or equal to x, but I can't have, let's say, a situation where I've got w, which is super high dimensional. So this is w, and then this is x, which is lower dimensional. But imagine w only sees, let's say, this part of x. And imagine that it's, in fact, this part of x here, the green part, which influences a and y. Well, obviously, that's not going to work, right? Because the part of x that I'm seeing is not the part of x that I need to marginalize over in order to find the effect of a on y. So that's not going to work. So this is the assumption that we're making, that w and z have to be a noisy view of x, but they have to be a noisy view of all of x. So hopefully this has demystified how it is that w and z are able to recover the causal effect of a on y under this unobserved x. Are there any questions about that before we go on? Great. Okay. So I think this is quite remarkable, because effectively, like, we know that W on its own isn't enough, but it's really interesting that W and Z together become enough. And this is something that is a reasonably recent discovery by Yao, Geng, and Jetkin in 2018, and so it's something that I think is quite an exciting development. Right. So I've demonstrated these proxy variables in the case where everything is categorical and finite dimensional, but I've got the aim of applying these methods in the real world, where my treatment might be like a fitness program, or it might be some method for highlighting important emails, or something that's much more complicated than just some small number of categories. So how is it that we implement this in the real world, wherein all of our variables might be high dimensional, and we need to find some smart neural net features of them? So that's what I'm going to talk about for the remainder of this lecture. So once again, we can address this problem in two settings. So we've done it using kernel methods, and we've done it using adaptive neural net features. So the kernel methods were by these very talented authors, so Afzaneh, Yuchen, Limor, Anna, Ricardo, Matt, and Krikamal. So they're the authors of the kernel part. And then the deep proxy part was done by Liuan and Heishiro. So these are the talented authors responsible for what you're going to see. The code, again, is available for both methods. These are particularly troublesome to implement, so I definitely recommend that you use the code if you want to try these out. Okay, and as before with the IV, we're going to focus on the adaptive neural net features for the remainder of this presentation. Okay, so we're going to proceed as follows. So, this is the hardest part of the course, so I'm going to go slowly, and I really urge you to ask me questions if anything's not clear. So first of all, we're going to describe the proxy relation for the continuous variables. So remember what the proxy relation looked like for the discrete variables. This is the proxy relationship for the discrete variables. We now need to instantiate that when W, Z, A, etc. are continuous valued. Okay, because here it's just like a bunch of matrices multiplying each other. We need to say what it looks like for continuous variables. Once we've established what the proxy variable looks like for continuous variables, we need to define a loss function for it, right? What is the loss that we need to minimize in order to recover this, this H matrix or function? Next, knowing the loss function, we need to define a regression for that loss. In solving that regression, we're going to do a second neural net regression. So we need to actually define two regressions, not just one. So that is going to be the plan. All right. So let's look at what the proxy relation looks like in the setting of continuous variables. So this is the vanilla average causal effect that we've now seen many, many times. I take my expectation of y given a and x, I marginalize over p of x, and then I get my average causal effect. But we don't observe x. Now this is what the proxy relation looks like in the general case with continuous variables. So I have a function this time, rather than a matrix, a function of w and a, and then I take the conditional mean of that function over w given az, and then I get y given az. So remember from a couple of slides ago what this looked like, right? This operation here is sort of like taking the conditional mean over w given az of this thing here. Well, it's literally like doing that. And so now I'm just doing that, but in a continuous setting. And I'm aiming to estimate the mean of y given az rather than the density of y given az, because it's the mean that we're interested in for this problem. So you can see that there's no blue in here. So I'm going to try and find this function which has the property that if I take the conditional mean of w given az of that function, then I get y given az. And if I find that function, then I'm able to estimate the average causal effect by taking that function, marginalizing it over w, and then that's my average causal effect. Now, there are conditions, right? I haven't written them down because they are notationally burdensome, but the conditions sort of have the same meaning as the conditions that we applied in the discrete case, which is to say that the z and the w have to be a sufficiently rich view of the x. So there can't be, let's say, dimensions of the x that are relevant to predicting y from A, but which we don't observe through the sort of noisy lens of our z and our w. So it's very much the same sorts of conditions as we applied for the discrete case applied in the continuous case. It just requires more notation to get there. But the discrete case gives all the intuition you need in order to understand what's going on. So this is what we're trying to solve. So this is great. Like if we could solve an H which linked these two things together, then we would be able to estimate average causal effect. So this is our challenge, right? We need some loss function on H, which if we minimize over H, we're going to recover the average causal effect. So what does that loss look like? Okay, so here is a loss function, which I claim if I minimize this over H, I'm going to obtain the average causal effect. So can anyone guess why that's the right loss? So a way to understand this is a squared loss, right? Let's say, forget about this conditional mean here, like this is just adding complexity. Let's say that we have solved the following problem, right? I'm going to take the expectation over y, a, and z of y minus f, a, z, right? What is the f that solves that problem? Well, the f that solves that problem is the conditional mean of y given az, right? That's what a squared loss does. Now we have claimed that the conditional mean of y given az takes this form, right? It takes the form of the conditional mean of w given az of hy, right? So if I take this form here and substitute it in there and minimize it over h, then I'm going to get an h which satisfies this relation, right? That is what that loss is going to do. So this is why this is the loss to minimize over h, assuming I've got this right, in order to get a correct estimate of my y given az. So we have a loss function now. All right, now we need to parameterize our loss function. We're going to, again, parameterize our loss function using neural nets and linear final layers. So here is the parameterization of our, we need to parameterize our link function, I should say, hy of a and w, okay? And we're going to parameterize our link function using neural nets features with a linear final layer. And we're once again going to use this formulation here, this Kronecker product formulation, which amounts to saying that we've got a very long list of features, which are pairwise products of features of W and A. So feature 1W, feature 1A, feature 1W, feature 2A, and so on and so forth, right? So a long list of pairwise products. We've sort of discussed in the continuous case that this isn't too damaging. But of course, in this case, we're using neural nets. So you might, again, wonder, as before, why not just use a single neural net taking W and A as input, right? Why bother using these separate neural nets for W and A? The answer is we're going to see rather soon why that won't work. Okay, so basically, this is the feature representation that we use for W and A, and we got a linear final layer here in order to make everything work out. And we're going to see why it is that we need both this feature representation and the linear final layer. But I think some of you can already start to guess based on the previous slides where we're going with this. Okay, so here's our goal. We want to map from W given AZ to Y given AZ using this link function H. We've said that this is the correct loss to minimize, right? Y minus EW given AZ of this integrated over Y given AZ. You know what this is. This is the sum of the squared coefficients of the final layer, which is a stabilizing term. So this is the regression that we need to solve. So once again, we need to get the conditional expectation over W given AZ of this H. And we can sort of ask the rhetorical question, well, how do we do that? Do we learn a model to sample from W given AZ? Like, that's a hard thing to do, and replace that sample average here. Well, in the setting that we care about, W might be high dimensional, so it's potentially quite difficult to learn to sample W given AZ, but we don't need to, as before. So again, as with conditional average treatment effect, there is a trick. So you'll probably remember this trick. Remember that we've said that HY of W and A is a linear sum of this Kronecker formulation, where I've got features of W and features of A. I need to take the conditional mean of W given AZ of this, right? So I do conditional mean of W given AZ, conditional mean of W given AZ. And now, as before, with the conditional average treatment effect, I can take this expectation inside because of the bilinear form of my feature representation and this linear final layer. So this modeling assumption that we made is essential in order that we can use the conditional feature mean to take this expectation here. If we didn't have this representation, so if we didn't have the linear final layer, and if we didn't have this tensor, this Kronecker product formulation for our features, then we couldn't do this trick, right? And then we'd have to learn a generative model. So I should say, like, this idea of learning a generative model is not an invalid approach, and there have been papers that have done it. But I think that that is solving a harder problem than you need to solve, right? The only problem you need to solve is the problem of getting this conditional feature mean. So I would argue that, just do that and don't do anything else. I think that's enough. All right. So this is the conditional feature mean. So, how do we get this conditional feature mean? Well, once again, we do ridge regression. And in particular, we're going to regress from A and Z using a linear final layer to the conditional mean of W given AZ of my features of W. All right. So how do we do that? So we're going to call this a secondary regression. So this is the orange regression because it pertains to the orange variables. So the ones for which assumption one holds, right? I want to regress from features of A and Z to the conditional mean over W given AZ of my features of W. There's only one algorithm in this talk, it's ridge regression. So here is my ridge regression loss, which is mapping from AZ to W. So by definition, this is going to give me an estimate of the conditional feature mean of W given AZ. Here, by the way, I don't have to break up my features of A and Z. I just use a single neural net that takes as those features as input because I don't have to do any further decompositions. All right. And as we know from before, we can get F, this linear final layer, in closed form with respect to my features theta and my features zeta. All right. And then we can substitute that in and backprop through Cholesky in order to solve for zeta. But as in IV, we cannot solve for theta on this secondary problem because theta is the output, right? If I solve for theta, I would be cheating. I'd make my thetas such that these features are 0. It would be a very easy problem, but it would be a very boring one because it wouldn't be any use for the problem that I want to solve using this F. Okay, so I can plug F into my stage 1 loss. I backprop through Cholesky for zeta. Okay, so what is my final algorithm? I first solve for this F explicitly in terms of theta and zeta. I backprop through Cholesky to solve for zeta. Then, as in IV, I solve for gamma in terms of the output of my secondary regression and these additional features here. So this is a difference compared with IV, right? In IV, we just had this term here. In the proxy setting, we both have the conditional mean of W given AZ, which is given by this estimate here, but we also have these additional features of A, which have their own parameter psi. All right. Then we substitute this in. We backprop through Cholesky to get theta and psi here. But what we, again, keep in mind is that this secondary regression, the linear final layer, remains correct, which is to say that even as we adjust the green parameters, we still have the correct conditional mean of our stage 1, for the current value of our zeta here. So again, this ensures that when we do that optimization in our primary regression, which is to say in our green regression, we keep the correct answer for our conditional mean for the current values of our input features. All right. And then as in IV, we iterate between the primary and the secondary features until convergence. And it's a min-min problem. So this is a reasonable and stable approach. Okay, here is a key point, which is that I sort of argued that it's a harder problem to sample from W given AZ than it is to estimate the conditional feature mean, because it's the conditional feature mean that we actually want to solve for. But I'm going to make an even stronger statement here, which is that I'm actually learning the features of W that are most useful in my primary problem. So let's say W is super high dimensional, but all that I need is those features of W that are most useful. If I go back a couple of slides, I only need the features of W that are most useful in my primary regression setting here. So in other words, like, I've got these features of W. I'm actually adapting those so that I can solve for Y given AZ as effectively as possible. So even if W is super high dimensional, I'm learning useful features of W for the setting that I care about. So in a sense, like, these features of W are both, predictable from AZ in my secondary regression and predictive of Y given AZ. So those features are kind of adapted to the problem that I'm trying to solve. So I'll pause here. Are there any questions about this? Because this is a fairly complicated idea, so I'd like to make sure that people are comfortable with it. Or if there are any questions, I'm happy to answer. Yep. Yeah, so I think that's an interesting question. Like, in a sense, like, we've got this sort of great big blob, right? Where, in a sense, things are kind of complicated is, the best zeta for a given theta and psi is going to depend on theta and psi, which are going to depend on zeta, which are going to, yeah. So I think there is an approach of implicit differentiation, which is able, at some computational burden, to like jointly optimize over everything. We have ended up doing this alternating approach, and I think we're quite comfortable with that, but we are not, let's say, sure that it's the best approach. So yeah, this is, I would say, a somewhat open question, yeah. But yeah, I think it would be interesting to explore, yeah. Are there any other questions? So we've obviously tried this out. So in the dsprite example here, so this is an instance of the setting where our variables are going to be high dimensional and are going to require neural net features. So we've, let's say, published results here, which are in a purely synthetic setting. So obviously, it's more interesting to apply this in practice, but these are the synthetic experiments. So in this case, we have as our hidden variable a number of variables, scale, rotation, pos x, pos y, which describe the position of a sprite. Now, what we do is we add a small amount of noise to that, and then we get our A. So this is our action in response to this hidden x. And then y, which is going to be a quadratic function of A with some multiplicative confounding by pos y, which is in this hidden x, because remember, x has a direct arrow to y. So what you're going to notice about this is that the treatment here is high dimensional, right? It's a sprite, it's in high dimensional space, and we're going to have to learn some neural net features of that A in order to determine the causal effect of A on Y. Now Z is going to be basically an incomplete view of these x's, scale, rotation, pos x. W is also going to be an image, right? And W is going to be a noisy image, which is going to share the same pos y as the clean image. But all of the other variables are going to be generated at random. And so what we're going to have to do is to extract neural net features of W and neural net features of A in order to find the treatment of a new image on my output. okay? And we're going to be doing that using the methods that I've described. So what we're going to compare against is an autoencoder approach. So remember that I said, like, don't meet your heroes, don't model your latents. If I were to model my latents, right, then in principle, I could recover the average causal effect, right? Because I've got my X here, I've got my W, I've got my Z, A, and Y, right? If, let's say, I were to have a reconstruction of my X from all of the stuff that I observe, then I could use that reconstruction and average over it in order to get my average causal effect. That's a valid approach. So what might be a pitfall of this approach? Well, the autoencoder doesn't care why it is that it's learning this latent, right? It doesn't know what it's using it for. And so what it cares about is reconstructing, what it sees as well as possible, regardless of how useful or not it is in estimating the average causal effect. So there can be circumstances, for instance, when, let's say, the W is very high dimensional, where this reconstructed space will use a lot of capacity in reconstructing what it sees to the cost of its, let's say, estimate of the components of X that are required in estimating A and Y, right? So, there is no, let's say, good reason why the latent space of an autoencoder should be relevant if your goal is to estimate average causal effects. By contrast, I think the approach that we're using, it doesn't try to reconstruct the hidden at all. All that it does is it sort of regresses from Z and A to W and then maps that regression to a regression from Z and A to Y. And that mapping is what you use to estimate the average causal effect. So it's sort of directly targeting at the problem of estimating causal effects. So autoencoders, it's not that this method doesn't work at all. Sometimes it works, sometimes it doesn't, but it's sort of the luck of the draw. Like if you happen to get a good latent space for the problem of causal effect estimation, then it works. If you happen not to, then it doesn't. So this is perhaps an argument to be a little bit cautious when you're using autoencoders for average causal effect. Okay, and we see that here. So obviously, this is a setting where we found that the autoencoder does especially badly. So on the x-axis, we have the size of the data set, the number of points that we've generated here. On the y-axis, we sort of see mean squared error of the estimate of our function on an out-of-sample setting. And what we're seeing here is that our approach here with the deep features is outperforming, in fact, quite substantially the autoencoder approach here. What we're also comparing against is the case where we're using various kernel methods for this setting, but the kernel methods aren't great when our A and our W are sprites. So they're also doing worse than the approach that we're proposing. So this is, I think, a nice setting where the approach that we're proposing is doing especially well. All right. We also have an estimate or a setting where we're doing policy evaluation. So obviously, average causal effect is all well and good, but in practice, what we're interested in very often is the problem of evaluating policy. So in the email example, right, our future policy isn't just, highlight the first email in your mailbox. It's highlight the relevant emails in your mailbox, which are the ones with which you should deal with greatest priority. So in this example here, we've made our policy depend on Z for this example. And the treatment A is ticket price. So this is actually all, relatively low dimensional real valued quantities. Nonetheless, in this setting, we're going to outperform the kernel and neural net approaches in evaluating policy. So this surprised us a little bit, but it seems that the neural nets are learning better in this setting. So it is what it is, yeah. Okay. So just to summarize, we are doing causal effect estimation with unobserved X. So, just to remind everyone what we had to learn, we need both an outcome proxy and a treatment proxy. So the outcome proxy, one can think of as being a noisy view of X before the action A is taken, and we can think of Z as being the noisy view of X after the action is taken. So the example that I gave here is a noisy inbox before the user interacts with it, and Z, the noisy inbox after the user interacts with it. Now, the key message is that don't meet your heroes, don't model your latents. Another key message is don't try to generate all your Ws, right? I needed the mean of a function over W given AZ, but learn your conditional feature mean. Don't try to learn to sample from W given AZ, because that's a harder problem than the problem you need to solve. And finally, ridge regression is all you need. So everything that we did here, we did using ridge regression. So again, the code's available, so I encourage you to use it. So yeah, so I'm happy now to take some questions.
Yeah, let's thank Arthur again.